Hello everyone, my name is Dr. Prashant Bople, and in this lecture we will cover extended Kalman filter and its application. So this lecture is basically prepared for MTech first year control system and power system from VGTI College. So when to use extended Kalman filter? So discrete linear time Kalman filter, in our previous videos we have seen it based on two assumptions. First, it assumes that the system plant is a linear. That means its behavior is linear. And second, the process is Gaussian. The covariance matrix is Gaussian. So in this linear Kalman filter, we see a process model and a measurement model where current state is passed through process matrix A or F, and to obtain the next state, a control input U is applied through control input matrix B. Then to obtain the measurements, we apply a measurement matrix H or C in other cases, and control input U is again applied, and we'll get an output ZK. So when a process noise is added in the process, which is a very practical thing, when a process is running, or some kind of noise, sensors noise, inbuilt circuit noise, a white noise, environmental noise is being added, then the output or states become noisy, which will give us a noisy XK. And when there is a noise added in the measurement part, like sensor part, then the measurements become a noisy measurement. So we are talking about when to use extended Kalman filter. Extended Kalman filter will work in a real-time plant. Okay, so real-time plant are always non-linear. As we always see, the plant behavior or any circuit behavior is not always linear. It has some kind of non-linearity. This non-linearity is being taken care by extended Kalman filter. So extended Kalman filter takes it assumes that process model has a function f which used to transfer the state xk and to next state xk plus 1 or xk minus 1 to next state xk by using control input uk, and the measurement part is again a function h which uses current state xk and use the function h to obtain the current measurement zk. So extended Kalman filter uses control input U and the noisy measurement which are being corrupted at the part of a sensory noise, and it will obtain a noise-free state estimation and noise-free measurement estimations. So in extended Kalman filter, the process model or the measurement model, or in other words, states transition model and observation models, are not linear function, but they are a non-linear functions, and they can be a differential equations also. So these functions you can see in this slide that f is a non-linear function which is differential equation of xk minus 1 and uk. By using this function f, the current state xk or previous state xk pass through the next state xk. But also at the time instant k, the process noise wk is added, which is having a mean of 0 and having a Gaussian type of noise distribution and a covariance of qk. And the measurement function h is a function of current state xk, which gives us a measurement at state of state as zk, and the measurement noise vk is added at time instant k, which is again having a zero mean and Gaussian distribution and rk as a covariance. And yes, uk is a control input. So till this point, we have understood when to use extended Kalman filter. It will be applied when non-linear system are there or a real-time plant behavior is a non-linear. So now we'll understand why linear Kalman filters cannot be used when the system is non-linear. To understand this thing, you first need to understand this figure. In this figure, we can see a linear function g of x. In this figure you can see y is equal to g of x is here. So this function is linear. So we are talking about a linear system over here, and we have some input x, and that input is being transferred by using some function g, and we are getting output y. So y is equal to gx is a linear function in this figure number 2. Okay, so the input, whatever input we are considering, should have or will be having some distribution or covariance. Now when this covariance is a Gaussian covariance, and when it is transferred through this linear function, is being transferred through this linear function, and we are getting output obviously. So the output will again have a Gaussian distribution. So when input x is having a covariance which is a Gaussian, and when it is transferred through the linear function, say y is equal to g of x, then the output y will have a covariance which is again a Gaussian. So that is a basic assumption where what was used in a linear discrete time Kalman filter, that input output are Gaussian, and the function which is being transfer function, that function is a linear function. But what happens when the system's function or behavior is a non-linear? So in this figure number 3, we can see a blue color line which is a function y is equal to g of x. So this function y is equal to g of x is a non-linear function, which can be seen in a blue line. So this can be of any shape, any kind of a non-linear shape. So when x is being transferred through this function g, which is a non-linear, and we are getting output y, then that output y won't have a Gaussian distribution. It can be seen in from this figure also, that the input x is being transferred through this nonlinear function, and we are getting output y, but that output will not have a Gaussian distribution. Instead of being Gaussian, the output will have some non-Gaussian type behavior, as you can see from this figure. So the input output Gaussian behavior criteria won't be satisfied as per the linear Kalman filter expectation. That's why the linear Kalman filter fails in case of nonlinear plant behavior. So what is the solution? I mean, yeah, there is non-linearity in the system, and again we want to estimate the states and want to get rid of the state process noise and get rid of the measurement noise, and want the noise-free states estimation. And again, have to deal with this non-linearity. So in that case, there is a solution which is called as a linearization. So what extended Kalman filter do is it linearizes the non-linear plant locally. So if you can see in this figure, figure number 3, when we have a Gaussian input x, and its covariance Px as a Gaussian, and in previous case when it was transferred through the nonlinear function, the distribution won't have a Gaussian distribution. But if we linearize as using Taylor series approximation using this red line, and then we transfer this input x with its covariance Px, sorry for the mistakes in drawing. So when we transfer it through this linearized model, then we will having a linearized Gaussian distribution as in red color. So we can see this linearized red color distribution, which is again a Gaussian distribution. So A Gaussian input px plus a linearized function gx in red color will give us a Gaussian output covariance. So how to use this extended Kalman filter? That the linearization part, we use a Taylor series expansion. A Taylor series expansion is nothing but a representation of a function as an infinite sum of terms that are calculated from the values of a function's derivative at a single point. So, in a simple word, any nonlinear function can be represented as a sum of infinite terms with some factorial or some power series. Okay, so any function f of x, as you can see in this figure, any function f of x can be represented as a function value at point a, its first order derivative, and a difference of x minus a, then second order derivative and upon 2 factorial and the difference square, and again third order derivative, fourth order derivative, and so on. This infinite sum and its derivative, when it's added, it will represent same as function f of x. Like sine of, if you can see the Taylor series expansion of sine of x, you can see the addition of term 1 x to 3 third factorial upon 3 factorial and other terms, and that power derivative. When we calculate the value of any of all this derivative at some particular point, we'll again get a sine function. So a function is divided into infinite terms. Okay, so in linearization, in what we extended Kalman filter, we discard these higher order terms and only use this first order derivative term. So function f of x can be represented as the first order derivative f dash of x. Obviously the value of function x at initial point, this value will be 0, and function f of x can be represented, this function f of x can be represented as the first order derivative f dash at value a. Okay, so using this first order derivative and neglecting higher order derivative terms, we can simply linearize this nonlinear function f of x into first order derivative. So the first order derivative of a function being used in extended Kalman filter to linearize the function is known as a Jacobian. A Jacobian matrix can be created by partial fraction or partial derivative of any function f, any nonlinear function or linear function f, being applied on any state x or state vector x. So you can see if the function f of x is a real valued function, then the Jacobian matrix J can be calculated as partial derivative of f with respect to x1, partial derivative of f with respect to x2, and so on. And that function f is a stack of values or vector or a stack of function, then that Jacobian matrix can also be calculated as a partial derivative of f1 with respect to x1, partial derivative of f1 with respect to x2, partial derivative of f1 with respect to x3, and so on till partial derivative of function f1 with respect to x1. And again other rows and remaining rows can be calculated, and the last term is partial derivative of function mth function with respect to nth vector term. So this matrix, Jacobian matrix, is m cross n matrix when the function is a mapping of n dimensional input to m dimensional output. So in a simple word, if x is the input having n dimension and y is the output having m dimensional vector, and the function f is being used to transfer x to the y, like y is equal to f of x, then the Jacobian matrix will be having dimension m cross n. to understand Jacobian, we first take a simple example that function f is a function which is making second dimensional real points to other second dimensional real points, and having function f1 as x1 x and y, and f2 is another function which is function of x and y, and that function f is x square y, and second function is phi x plus sin y. It's like a simple A matrix. Y is equal to ax plus bu. In the function f is used, we'll use x and y terms and give some output other terms. So function f1 is there, x square y. Function x2 is there, phi x plus sin y. So Jacobian matrix J, which is again a function of x and y, can be calculated as partial derivative of f1 with respect to x, the by the x, in other words the by the y, and second row second column till that point the by y. So the Jacobian matrix is 2x x square 5 and cos y. And yeah, determinant of this Jacobian matrix can also be calculated as 2xy cos y plus 5x square. So this is a simple method where a function is there which is mapping some dimensional n dimensional input to m dimensional output, and we can calculate a Jacobian matrix J. So based on this Jacobian matrix algorithm and linear Kalman filter algorithm, extension of linear Kalman filter is given as an extended Kalman filter, where instead of using nonlinear function directly, we linearize the function and use this function linearized matrix, Jacobian matrix, to calculate the covariance. The reason is this, what we understood from the previous figure, why this linearization is important, that a Gaussian covariance cannot be used for nonlinear function. So the Gaussian covariance can be transferred through only linearized function, and that function has to be linearized. So in that case, only in that case we'll get a Gaussian covariance. So extended Kalman filter again works on the same principle of a linear discrete time Kalman filter, that prediction and updation. So in prediction case, we first predict the next state, that x had k given k minus 1, when previous state x had k minus 1 given k minus 1. That means a previous state. So previous state is transferred through function f and control input u, and the next state is predicted only. And that again covariance matrix is predicted by using f and p, k and ft and q. So what is f? F is Jacobian matrix. We'll see later in this slide also. Now the innovations is that is the error between the predicted state and the measured noisy set zk is calculated as a y tilde, and innovation residual is calculated xk by depending on hk, pk, ht transpose plus rk. Rk is covariance matrix of measurement noise, and qk is covariance matrix of process noise. Now the Kalman gain kk calculated using predicted covariance pk and the innovation matrix. So this Kalman gain k will be used to correct the update the value. So the predicted value x had k given k minus 1. This value is taken into consideration, and this value is updated using Kalman gain kk, which is calculated, and the innovation, that is error between measured state and predicted state. So using this error and Kalman gain k, the current estimation is updated, a current predicted value is updated to updated state. Again the covariance matrix is also has to be updated. So PK matrix is updated using using Kalman gain K, H matrix and PK matrix. So Fk is nothing but a Jacobian of function f, which is a linearized function, linearization of function, non-linear function, and H is Jacobian of H matrix, H function, which is a measurement function. So F is process function or state transition function, and H is measurement function, and capital F is Jacobian of the same function, and H is Jacobian of the measurement function. Now, to understand the extended Kalman filter algorithm more clearly, we'll take a MATLAB example where a problem statement is given with a process model and a measurement model, and some initial conditions are given. So the process model is some function of xk, where first state is xk, first x1, and second is x1 x2, multiplication of x1 x2, and the measurement model is just h of xk, which is the measurement of second element. Now initial conditions are given like 0.9416, and that is a complex number. Now to implement this in MATLAB, first we will take a clear out closure and CLC command, which will clear out previous states and previously stored variables. Then the initial conditions will be loaded in the MATLAB, that how much time instance we want, like if for in this example we are taking 100 number of time steps. Then the function f of x, that x1 x2 x1 and x1 x2, and the measurement model as a function h will be stored as second element x2. Now initial condition x is given. For same prediction model and updating the state, we need the initial condition, because the for loop will be continued in from next to next states. So the initial conditions for predicted and updated are stored as a same as initial condition of original state. You can change these initial conditions when you run the program to understand the feasibility and the track, how fast the extended Kalman filter can track. So to check that those things, we can change the initial conditions for predicted state and updated state also. Then a covariance matrix initial condition is stored as a diagonal matrix, and yes, obviously the noise and the covariance of noise matrix, and for the process noise, like Q is process noise variance, and capital Q matrix is process noise covariance matrix. Again, R is 10-20% of a mean noise. That's why 0.2 is taken, and capital R is again covariance matrix of this. Now to implement the actual plant, we will take whatever the number of states for in a for loop, and we'll apply a function in a iterative process, and from the initial condition we will take iterative process and store that element as x and y, and we will plot that result, and when we plot this result we will get a damp sine wave. Then we will add some noise in this states. So the we will start with some initial condition and add some process noise using q star random n number of MATLAB command, and again measurement noise will be added as per the initial conditions. Then we will plot this noisy signal on over the. Now in continuation with the program, we'll implement the extended Kalman filter algorithm, where k is varied from 1 to n, and in between this for loop we will implement the actual algorithm of extended Kalman filter, where Jacobian matrix is used, linearized matrix f and h are used to calculate the p matrices. Then predicted values are updated using Kalman gain. So this will be the process. So f matrix, Jacobian matrix f is calculated here, then h matrix is calculated, then the p matrix is calculated using this Jacobian matrix f and h. Innovation s is calculated, and Kalman gain, finally Kalman gain is calculated using this predicted covariance matrix, the linearized measurement matrix, and the innovation. Then a predicted value is calculated for a given state, given previous state, and the measurement value is predicted, and these predicted values are updated using Kalman gain k, and innovation. So in this diagram you can see, in this code you can see the predicted value is here. This predicted value is calculated in previous states. This predicted value is updated using Kalman gain k, which is calculated here, and the updated value depends on the noisy measurement, which is a noisy measurement from actual plant, and a predicted value. So the error between noisy measurement and predicted value, this is a predicted value at this line. So the error between predicted value and measured value is multiplied with the Kalman gain, and the predicted value of states are updated. Similarly, the measurement values are updated. And yes, P matrix, which is initial case when we have started, was a diagonal matrix of 2 dimension in this example. This will be updated for from using this Kalman gain k and innovation matrix, and updated matrix is again stored in p value. To plot the results, we plot the updated value of y matrix, and in this figure you can see there are three graphs in this figure, where the actual red line, if we are able to zoom this part, we can see the actual red line is actual plant behavior. Then the blue line is noisy measurement, and the black line, dotted black line, you can see is uh, updated updated values using extended Kalman filter. So what's happening here? Here, the actual, if we forget about the actual plant behavior, we are only having a blue line measurement, which is a noisy measurement. From the noisy measurement, we will use extended Kalman filter and predict the actual plant behavior, which is black dashed line, and that black dashed line is actually matching with the original plant behavior. So we are able to suppress the noise from the measurement. We are able to actually predict and update the values of states. So similar graph can be drawn for for x1 and state 2, and we are able to see the how the system behave. So thank you for listening, and implement this extended Kalman filter algorithm with this simple example. Thank you.